Hello and welcome to another video, this time looking at algebraic proof. Can be a bit of a tricky topic, but hopefully this will help kind of understand the bits that make it up and hopefully some ideas to help you get started as well. I'm going to start off looking at just some statements that I think are really helpful to know when you're doing algebraic proof, and to kind of help you start each question and hopefully get a few marks on each one. So starting off looking at 2n. Now we're going to need these statements to help us represent different things that might be part of a question. And the first one is, if I think about n just being any number, then what must two lots of that number be? So if you think of some examples for n, like if n was 1, then it would be 2. If n was 4, then it would be 8. And essentially whatever you put in for n, this will always end up being an even number. So 2n we can use to represent any even number. If you continue that to 2n plus 1, well, if 2n is even, then if you add 1 to it, then that must be an odd number. So if a question ever says an even number, you can use 2n. If it ever says an odd number, you can use 2n plus 1. And they'll always end up being even or odd, which is quite useful. The next one, well, if you think about n being any number, then n plus 1 is the next number along, n plus 2 is the next number along. So we use these to represent consecutive numbers. Consecutive numbers because they just follow in a sequence. So if you had n plus 3, that would be the next one, and you can have as many of them as you need. Next one, if we have 2n, well, we know that's even. So 2n plus 2 is an even number plus 2 more, so that's the next even number, and then 2n plus 4 will be the next one after that. So these are the consecutive even numbers. Oops, consecutive even numbers. If you ever need consecutive even numbers, you'd use those, and you kind of get the idea that 2n plus 1, 2n plus 3, and 2n plus 5 are going to be the consecutive odd numbers that follow along from there. So we've kind of got the idea of how to represent an even number, how to represent an odd number, consecutive ones, consecutive even, and consecutive odd. The last one's just a few examples just to kind of highlight normally a way to finish off a question. If n is any number, then 4 lots of that number, that must be a multiple of 4. And you can try that, just put any number you like into n, you end up with a multiple of 4. And the same idea for this one, 3 lots of n plus 1. Well, it doesn't really matter what n plus 1 is, you'll end up with a multiple of 3 at the end. And 8n plus 3 again, whatever's in the bracket, whatever that comes out as, if you times it by 8, you still end up with a multiple of 8. So these are basically just some statements to help you start a question, and quite often they'll ask you to prove say the sum of 2 even numbers. Well, then you'd need to have 2n for one of the even numbers and say 2n plus 2 for another even number, or something like that. And hopefully that'll be enough to get you started. And this idea at the bottom is more useful for the kind of end of a question, but you'll see in the examples we do that these statements end up being quite helpful. So, first example. Prove that the sum of 2 consecutive square numbers is an odd number. So again, we got this idea of consecutive and squaring them, and at the end coming out with an odd number. So let's think, well, how do I get 2 consecutive numbers? Well, that's n for one number, and then the next number along is n plus 1. And then, well, how do I get square numbers? Well, that's n squared is a square number, and n squared plus 1 squared is also a square number. So this is consecutive square numbers, just the next 2 along. And you can try that. So if we said, say, if n was 2, then this would be 2 squared plus 3 squared. So that's 4 plus 9. And if we try that, you can see that that ends up being 13. So this works. This will end up being a odd number, but to prove it, you can't just state an example. We need to show algebraically why it works. So if we go back to that original line here, n squared plus n plus 1 all squared, well, how are we going to show that this is always odd? Well, we can't really simplify n squared, so let's keep that. But we can simplify the second part. If I make this n plus 1 multiplied by n plus 1 and expand that out, you get n squared plus, multiply the first bits, we get n squared plus n plus n plus 1. So that's just that expanded out using whatever method you like. And if we simplify this down a bit, you get 2n squared plus 2n and then plus the 1 at the end. And you could use that, but I think it's a little bit nicer just to simplify that a little bit more. If I take out a factor of 2 from this, just the first bit, you could write this as 2n squared plus n, just by factorising those first two terms, and then add 1. And this is actually all we need to prove it. It's a good idea to have a little statement, but just to kind of highlight what we've actually achieved here. Excuse the colours. So this bit, that has to be an even number, because we've got 2 times something. It doesn't matter what this is. If we're timesing it by 2, it must end up being a multiple of 2. And then this bit here is just adding 1, but it really is odd. And if we add 2 numbers, one of them's even, one of them's odd, then our answer at the end has to be an odd number. And that is enough to prove it. It might be a good idea to write a little sentence that says an even number plus an odd number must make an odd number. But that's essentially what we've done. So we've answered the question, prove the sum of 2 consecutive square numbers, which is what we started off with here, a square number plus another square number. We just expanded it out and showed that it was equal to an odd number every time. Let's look at our next example. So for this one, they've actually given us the statement already. They've said show that 4n plus 1 all squared minus 4n minus 1 squared is always a multiple of 16 for positive integer values of n. So remember, positive integer values just means positive whole numbers for n, and we need to show that it's a multiple of 16. Okay, so how are we going to do that? Well, we're going to need to just simplify and see what comes out. So the first bracket, 4n plus 1 squared, would look like that. I'm going to write a big minus here to help me remember there's a minus, and I'm taking away all of 4n minus 1 squared, which looks like that. If we expand the first one, 4n times 4n is 16n squared. 4n plus 1 is plus 4n. Then we're going to get another plus 4n, and then a plus 1. Again, big minus sign to help me remember. I'm taking away this whole side. If we expand that, we're going to get 16n squared. 4n times 4n. 4n times minus 1 is minus 4n minus another 4n from 4n times minus 1, and then a plus 1. Okay. Now it would be easy to go wrong here. That's why I've made that minus sign nice and big. We've got 16n squared minus 16n squared, so that's going to cancel out. This would become, let me just simplify this down first. So that's 8n plus 1, and then we're minusing all of this. So it might be nice to put it in a bracket. Let's keep all of this here actually. So basically I'm just going back and I'm going to simplify these two parts before I cancel it down. Don't do too much at once. Minus 8n plus 1. We're taking all of this bracket away. And we'll just do it term by term. So 16n squared minus 16n squared, that'll cancel out. 8n minus 8n, so that's essentially the same as 8n plus 8n, so that's going to be 16n. And then plus 1 minus 1 will cancel out. So we get left with 16n. And we know what to do with this. We know anything times 16, this must be a multiple of 16. And you can try it. Any number you put in for n, that will come out as a multiple of 16. And I should have said, like I did in the last example, you can try this. You can put in a value for n, obviously use the same one on each side. And if you try it, it will always end up being a multiple of 16. It's a good idea to try and get your head around sometimes, just to try it with some numbers and see what happens, see if it works. Let's try our last example. Example number 3. So here we have prove that the difference between the squares of any two consecutive odd numbers is always a multiple of 8. So again, we're looking at square numbers and two consecutive odd numbers, so we know how to write those. Looking at the difference between them, and it needs to be a multiple of 8. So I didn't do this last time, but let's start off by just trying it and see what happens. So let's pick two consecutive odd numbers. Let's try 5 and 7 consecutive odd numbers. And we're going to square them, and then we're going to subtract them from each other. So 5 squared is 25, minus 7 squared is 49. If we subtract them from each other, you get 24, or minus 24, which is a multiple of 8. And we could try it with another one. Let's do about 1 squared minus 3 squared. So that's 1 minus 9, which is minus 8. Obviously, you could do this the other way around and you end up with positives, but you see that it will make a multiple of 8. So it works with regular numbers, but that's not going to be enough to prove it. So let's think, how do we write two consecutive odd numbers? So thinking back to our statements, have a look back at them if you've written them down. We wrote a odd number was 2n plus 1. And then we wrote the next odd number is 2n plus 3. And it says in the question we need to square them. So if we're squaring that one, remember we've got to square the whole thing. If we're squaring this one, square the whole thing, like that. And then we're doing the difference between them, so a negative. Okay. So let's see what that comes out with. As always, I'm going to write this negative nice and big just to help me remember that I'm subtracting the whole of this second bracket. So writing them out, 2n plus 1 times 2n plus 1, and we'll expand that in a second. Big minus sign, and 2n plus 3 times 2n plus 3, like that. So expanding it, 2n times 2n is 4n squared. 2n times 1 is plus 2n. 1 times 2n plus 2n. And then 1 times 1 is 1. And then we're subtracting the whole of whatever we get from this. So 2n times 2n is 4n squared. 2n times 3 is plus 6n. Another 6n. And a plus 9. Okay, so let's simplify those down. We get 4n squared plus 4n plus 1 minus, and then we have 4n squared plus 12n plus 9. And again, be careful because we're subtracting this whole expression here, this whole bracket here. So 4n squared minus 4n squared, that will cancel. 4n minus 12n, well, that's minus 8n. And plus 1 minus 8 is minus 8. Okay. If I'd written them the other way around, I wouldn't have had these negatives, but that's okay. So how do I show that this is always a multiple of 8? Well, if I factorize it, if I take out a factor of 8, we get 8 brackets minus n minus 1. And it doesn't matter what the inside of this is just any number. Doesn't matter what I put in for n. if I multiply that by 8, that's going to end up being a multiple of 8. Okay, because no matter what you put in, you will always end up with a multiple of 8 at the end. So that proves the third example, that the difference between the squares of any two consecutive odd numbers is always a multiple of 8. So there you go. Hopefully that was helpful. I think those statements are probably the main thing to remember. If I just quickly flick back to them. And you see that they kind of help you get started on the questions, and towards the end you might need to factorize, like I did on that final example, to just have any number and then timesing it by something gives you the multiples that you need. So hopefully that was helpful. If there are any questions, leave them in the comments.